To begin with, I'd like to show you a graph. It's a rather long graph. Could you hold one end? One of you, I think, if you hold it up. And sit down. No, like that. Thank you. It's a rather long graph, and I'm plotting the consumption of oil in the world against time, and I'm starting at the dot, or at least I'm starting at the birth of Jesus Christ. That's 500 years. Now you see, that's 1,000 years. You see it's rather a dull graph, isn't it? The consumption of oil is 0, or so nearly 0 that it doesn't appear. That's 1,500. That's 1,900, and something begins to happen. Would you like to come out and hold the other end? Something begins to happen then, and then it stops happening, and we get to the year 2100, 2500. How far shall we go? 3000. We'll all be dead by then, so let's stop there. Well, that may seem a long time, but after all, civilization started 5,000 years before that, and we hope the world will go on beyond 3,000. And look, that's the oil. A hiccup in history. And we're in just about the middle of the hiccup. At least we're on a good part of the hiccup at the moment. We're on the up part of the bend. How old are you? 10. So you see, by the time you are 35, you'll be on the downgrade as far as your oil consumption is concerned, won't you? And if you have a reasonably long life, you will be in real trouble for oil. Coal would help you a bit better. If I plotted coal on here, we would have a similar sort of longer hiccup, which peaked about 2,150 and then came down like that. But in the course of history, it's almost a perturbation. And we're very fortunate to be in it at the right time. But we have to look to even our own future, let alone other people's. And I want to talk today about how we're going to replace those supplies of fossil fuels when they run out. Well, we need our energy in 3 principal forms. We need it as heat, we need it as electricity, and we need it as chemical fuels. And you know very well that we can convert one into the other to some extent and to a certain degree of efficiency, but you can't run your television set on petrol. And you can't run your petrol engine on electricity. And so man does need energy in these 3 forms, and it happens that he uses them approximately 1/3, 1/3, 1/3. Admittedly, his electricity is made from fuel and much of his heat is, but that's how he uses it. So I want to ask, how can we use sunbeams to make these 3 forms of energy? And we, in the last lecture, dealt with that one. And you saw low-grade heat is about 40% of our needs, just over 1/3. And you saw how we could capture that last time fairly easily with black plate collectors and so forth. Today, then, I want to talk about the other 2. And to begin with, about electricity. How can we use sunshine to make electricity for us directly? Well, we can.
you've probably seen silicon cells, and you know that if sunshine falls on them, they do useful things, like running a radio or running a motor, and many other things, and I want to see how that happens. So these are silicon cells which were developed for space, and guess what they're made of? Silicon. Silicon. Yes, sand, you said, is silicon oxide. And because of that, silicon is the second most abundant element on Earth, so there's plenty of it. The trouble is there isn't much of this stuff. In fact, I've had this specially flown over from France so that you can see it. And that is a single crystal of silicon. Extremely expensive. It's extremely pure. It has to be purified so that there's less than 1 part in a million of impurity in it. And then it's grown by melting the silicon and gradually pulling it out in this boule, as it's called. Now that is cut across the edge here into little slices. And here's one of the little slices. And it's these little slices which we use to make these cells. And let me show you how they work. Silicon is rather like carbon. And it has 4 bonds, and it has 4 electrons around it. And here you see the silicons, each with 4 silicons around them. Now, having purified that beautiful crystal, one puts 1 part in a million, or a few parts in a million, of an impurity in it, like arsenic or phosphorus, which has 5 electrons. It fits very nicely into the lattice, but it has 5 electrons, so it wants to get rid of 1, and it gets a positive charge. So that's what you do with the bulk, and then you diffuse onto just a thin layer on the top of that bulk. You diffuse in another element which has only 3 electrons, like boron, and that is going to pick up an electron. So if you now put those two together, this is a thin layer, if you put those two together, there will be a charge separation across the edge. Perhaps you can just see the positive and negative charges across the edge there. Now suppose I shine light on that through the thin layer. It liberates electrons from the silicon, and they're free to flow. And where will they flow? Towards what? The positive or negative? Towards the positive inside, and therefore outside the other way. The electrons flow this way, so the current flows that way, and that's the positive pole. You stick a couple of wires on there, and you've got electricity from sunshine. And that's just what is done. What's happened to those cells? Oh, thank you. Now that's what is done. We now coat the slice here with metal on one side, on the other side with an anti-reflection coating, and we have to have a grid of metal on that because we have to get light through it, and that is what is used. That will give us a few hundredths of a watt, and then if we put them all together into an array like this, we can do anything with them if the array is big enough, of course. One cell doesn't give us very much power, but we can make, if we can afford it, and that's quite a question, we can make an array big enough to run a railway. In fact, Mr. Coates does run a railway. Here is the Coates railway. Is that the way around you want to connect them? All right. And would one of you like to run the railway? Who's a railway enthusiast? Are you? All right. Well, here's the light. Here's the power. There are 2 switches, so you can switch on both lights. Would you like to switch them on and point it at that? Not too near. Not too near. All right, switch them on. And another. We've got them both on. There we are. You're running the railway. Put it a bit nearer. Let's have a bit more light. See whether we can run him off the track. We did. That's a fine way to run a railway, and what's more, you'd need an awful lot of these. In fact, at the moment, of course, they're really useful for remote applications, rather special applications. One such remote application is Everest. There's nothing much more remote than that, and Mr. Coates' baggage here is what the BBC camera team took up Everest. I wouldn't like to carry it up Everest, but they had to charge their batteries, and they got tired of running down to Kathmandu or wherever the station was. By lugging this up in the first place, they could supply their batteries as long as they liked. Another very important application is to buoys at sea and remote beacons. Here is a picture of one that you can see on the screens. This is in the Channel. And this will go without any attention except topping up the batteries. It'll just go on and on for years and years, supplied by that battery of silicon cells, which you see in front of it. Well, talking of remote applications, what's the most remote place that man goes to? Space. Yes, and of course, the reason that we have silicon solar cells, and they're beautiful things, very efficient. The reason we have them is that millions of pounds and dollars particularly have been pumped into their development because of space and because of military interest in them. Otherwise, we almost certainly wouldn't have developed them as quickly as we have. And they are nevertheless useful in space for peaceful applications. And this is a satellite. It has been kindly brought here by the Royal Aircraft establishment. Mr. Dollery and Mr. Dunnett have set it up for us. The satellite is here, and this little package here contains some 20,000 little solar cells. Well, of course, they have to be spread out, and you can't shoot them into space like that. So this is a design which we put up into space, and then we fire it from the ground. Would somebody like to fire it from the ground? Do you like to do it? Well, okay. Well, the thing is that first of all, we shoot it up into space. We have to imagine we've done that, you see. And now you are in charge of the control at base on Earth. And this is your control panel. There are two. It's duplicated in case something goes wrong, right? You're going to switch on, what does that say? Safe. And that says? Armed. Armed. Well, you're going to arm it, and then you're going to fire it with that when we count you down. Would you like to arm it first? Just that, right? Now, when he fires it, he will actually fire a little through space, through a radio message, to about 20,000 miles up. He will fire, that's where it would be, he will fire a tiny little explosive which releases a catch. This is a very positive way of releasing a catch. A little explosive releases a catch, and then it'll be pushed up by air. We'll see what happens. So shall we count? What's your name? Martin. Well, Martin at headquarters is waiting to be counted down. Shall we count him down? 5, 4, 3, 2, 1, fire! He fired it. And here you see the silicon. Every one of these is a little silicon cell. You see them unfolding and unfolding. This happens in space. And there are two. This is one paddle. There are two paddles, one going up, one going down. You can't do this down here because there's gravity, you see. You have to treat it very carefully. But in space, there's no wind, there's no gravity. And so it has to be very, very light. There's practically no weight there except the cells, and they're being pushed up by the air, compressed air. It still going. What's the height, Mr. Dorry?
It's about 17.5 feet.
17.5 feet when it's finished.
This is for one wing.
That's just one, and then we have the other, and it's about 300 watts per per array.
Yes, that's correct. 300 watts per wing.
300 watts when it gets up there. Well, it's nearly there. Now, it's not all covered with solar cells. We've only put solar cells, or they have only put solar cells on the middle bit. But I wonder if, you see the blue part up there, would you like to shine a light on that now, if you can reach, you've got to be the sun now, you're a quick change. First of all, you're base control, now you're the sun himself. You switch on those, shine on there, and you see, it's really for communications. It's for messages, sending messages to space and back again. So let's shine the sun and see whether we get a message, okay? Switch both of them on and hold it up. You've got the whole weight? Switch them both on. Both on? Yes. Yeah, go right up to it. Right up to it. Well, let me see whether maybe you're not quite close enough. The sun, I'm a bigger sun. Are we getting the message?
Are we getting the message?
Well, who's up there? You know who, yes. Good, all right. Thank you very much indeed. Well, the trouble, those cells, which we've seen a number of examples of now, are as much as 15% efficient. Their theoretical efficiency would only be about 23%, and 15% has been reached in efficiency, which is pretty good. The trouble is they're very expensive. And people are trying alternatives. One is to use cadmium sulfide, this looks pretty much, most of them look pretty much the same to look at. That's about 6% efficient. And another way is to use silicon, which is really beautiful, but instead of growing this enormous boule, which is the expensive part of it, if you could just dip something into silicon, make a thin layer on carbon, for example, then that would be very much cheaper, wouldn't it? You could almost run it off like newspapers. You can imagine doing that. But then it wouldn't be one single crystal, it would be a lot of little crystals on the surface. Well, that has been done, and they have achieved, Philips Industries and the French LEP, who supplied that to me, have achieved an efficiency of 5 or 6% that way, and these are likely to be very, very much cheaper. So that's one approach. And another approach is to go away from this type of cell. These are called photovoltaic cells, after Volta. And there's another kind called photogalvanic, after another Italian, Galvani, who gave us the word galvanized into action because of his experiments with frogs' legs. The galvanic effect goes on in solution. And liquids can be very much less expensive. Now, you remember this experiment, don't you? Where I had a blue solution of dye mixed with some iron salt, and I irradiated it, and it bleached. A reaction went on, and then the reaction goes backwards. This will then go back to that color. And you will remember that I told you what was happening there was a transfer of an electron from the iron to the dye, like that. And then in solution, they came together. This was unexcited. They came together, and the electron went back. Now, suppose we have 2 electrodes in the solution, and suppose I do the same thing, and I transfer the electron to the dye, but now it manages to get to the electrode. This is unexcited now. It manages to get to the electrode before it gets to the iron. Now, if I connect those 2 pieces of metal, the electrodes, together, of course, electrons can flow, can't they? And it can flow over to this electrode here. And now the unexcited dye at this side can pick him off again. And we're back to where we started here. We can shine light on it again and do it. And the net result is we've pumped electrons through the wire, haven't we? Got current. Well, this is a possibility. And Isabel here, Isabel Ferreira, who is from Portugal and has been working in the lab here for 3 years and a lot of the time on this reaction, is doing this. She has in this cell a solution just like that one, and she divides the cell into 2 parts with a black piece of paper, black piece of card, and I'm going to irradiate just one side, and you're going to watch the meter as I irradiate it. And you see the current flowing, the meter's gone right over. And now if you look at the cell, you see I bleach one side and not the other. And if I'd irradiated the other side, it would have gone the other way. Now the trouble with that is it's very inefficient, because most of these ions that I showed you recombine anyway, just as they did in the beaker. They don't get to the electrode. And how are we going to make them get to the electrode better? Yeah?
By giving the electrode more surface area.
Yes, that would be very good, but of course if they're a long way away, they still have the job of getting there. Surface area per amount of volume is really the thing. In other words, if we can put them close together, and that's what we do. These are now the 2 electrodes. We put them extremely close together with only a little bit of dye between. This is metallized glass. And this is platinized, in fact. And this has some tin oxide on to make it conducting, but it's also transparent. So I put those 2 together, and you see they're connected. They have electrodes connected to them. And that's what Isabel has done here in this cell. It's just 2 of those. It's just held together by paper clips, and she's put the solution inside. And now we're going to see whether this one will work. Watch the meter again as I irradiate this, and you'll see a nice hefty current from that one as well. Now that one is 1.5% efficient, and the materials, apart from the electrodes, but the basic material, of course, is nothing. I'll give you some. It's very, very inexpensive compared with silicon. So all these are possibilities of getting electricity directly from sunbeams. Now, let's come. We've done electricity. We've said something about electricity. There are other ways, but I've given you a fair crack at that. Let's talk now about fuels. Because fuels are unique. Energy in fuel is much more valuable than all the other kinds because it can be stored. You can't store heat. You can store heat, as you know, overnight, or if you have a well-lagged tank, you can store it over 3 or 4 days, but not much more. You can't store electricity except as a fuel. If you store electricity in your car battery, you're really bringing about a chemical reaction, aren't you? And so you're storing it as a chemical fuel. So fuels, as nature discovered many years ago when it invented the leaf, fuels are the best way of doing things, especially since we're talking about sunbeams. And sunbeams have this disadvantage of being a bit unreliable, especially in this country. They come and they go out just when you want them. So if you can store energy, it's very important, and you store it as a chemical fuel. Now, how can we do that? Well, one way, of course, I'm talking about using sunbeams all the time. One way, I've already more or less told you. A jolly good fuel is hydrogen. And everybody, many people have this ambition to split water into hydrogen and oxygen. And they talk about the hydrogen economy because you could put hydrogen into the gas lines. And that would be wonderful when the gas disappears. Well, how can we do that? Knowing what we know already. Could we do it using this? That makes electricity. Can you make hydrogen and oxygen from water with electricity? Yes. You electrolyze it, can't you? Well, some of you know and some don't, so perhaps we better do it and make sure. Here I have just a couple of wires, metal electrodes stuck into some salt, and when Mr. Coates switch, and here we've connected them to this battery of cells. Now we switch on the light, Bill, thank you, and you see how copious supply of gas comes bubbling off there. Well, I wonder what that gas is. some of you know clearly already. Is it hydrogen and oxygen, or is it just air? Let's see. Let's collect a bit of the gas. This is a bit of soap that Mr. Coates put in my hand, and he's putting a few bubbles of this gas so that we can analyze it, or at least examine it chemically, into my hand. Okay, there they are. Can you see them? Now let's see whether they're air. No, it's not air. Air doesn't behave like that. It was hydrogen and oxygen. So there we made a fuel from sunbeams. But that's cheating a little bit, isn't it? Because there we were using electricity, we were making electricity and then making the fuel. Now, any chemical which we make by pumping energy into it, which has more energy than its products, which if you're a chemist you would say undergoes an endothermic reaction when it's formed, is a fuel, isn't it? So, and most unfortunately, most photochemical reactions go the other way. They're just catalyzed by light. They don't really store energy, but some do. And here is one which I'm showing to you simply as an example of how one can make what is really a fuel by shining light on a substance. This is a dye, it's an anthraquinone dye. Can't see much color in it. And I'm going to shine light on it. And it's just very like the reaction we've seen already with the blue dye. It will pull electrons from the solution and go and change color, I hope. Now, you may not see the color too well until I switch the light off. Perhaps you can see it already. Can you? Yeah? All right. Well, that's changed color. Now, that is hydroquinone. It's anthrohydroquinone because it's pulled electrons from the fuel, from the water, and this is water and alcohol. It's pulled electrons from those. Now, that is a high-energy compound. It has more energy than it had before, and it will react with air. If I let in air, it will burn. You won't see a flash of flame or anything, but it will get warmer as it reacts. Watch what happens if I let in the air. Now, the anthrohydroquinone, which is red, reacts with the air when I shake it and goes back. Goes back to anthraquinone, which is what we started with. And then we can do that all over and over again. Now, unfortunately, that is a very efficient reaction, very high efficiency indeed. In fact, nearly 100% of the quanta absorbed are stored as energy. But that is with alcohol present. And alcohol is a fuel anyway, and we're using that up. With water, the efficiency is way, way down. And that's the problem. But again, there are possibilities of making that work with water, and then we have a nice way of storing energy. The trouble is, you notice that wasn't colored. It's absorbing mainly blue and ultraviolet light, and this is the trouble. To break down water, and most substances like this, you need ultraviolet or blue light, and that's no good because you know where's most of the energy in the sun. What color? Green and out to the red. So that's no good. Now, if you're going to use those smaller quanta, remember those smaller photons that are out there, you've got to use 2 of them or more. And that's what the plant does. And so I turn now, first for a moment, away from photochemistry to photobiology, to the plant itself. Let us have a look. Let us learn from the brilliant syntheses that the plant carries out. Let's have a look at the plant, see how it does it, and then see whether we can do better. Shall we do that? It's sensible. In fact, let's first of all see to what extent we can use the plants as they are as energy storers. They're absolutely marvelous, some of them. They can make for us materials like wood and cotton and foods and sugar and so on, and they can even make petroleum. Do you know a plant that makes petroleum? Do you know a plant that makes hydrocarbons anyway? Yes?
Sugar.
No, that's a carbohydrate, remember? That has oxygen in it. Do you know one that makes just carbon hydrogen, rather like petrol? Well, rubber is just carbon and hydrogen, and the rubber tree does it. Here is, until petrol became so plentiful, we got all our rubber from rubber trees, and there's every chance, this is latex, just comes out of a rubber tree like that, and doesn't look like rubber, but I want to show you how like rubber it is and how little one has to do. I'm putting some methyl alcohol in it here, just to coagulate this milky substance, like this. And now I'll pick it out, and you see it's already partly coagulated, and I'll dip it in here and roll it into a ball. So, that's not a bad ball, is it? And it's rubber. Well, you see, the rubber tree is very productive. It produces a lot of rubber per acre. Why not use that? That's the sort of thing which we're going to have to do, because the petroleum doesn't just give us energy, it gives us our materials. And to make those materials from petroleum, you not only need petroleum, but you need energy as well. So we're saving petrol, we're saving oil in two ways if we can do this. And if we can use cellulose instead of synthetic polymers and so forth. But to return to energy, let us have a look at the sort of energy we can get out of the leaf. Back to the leaf. Let us have a look at the energy that we get out of the leaf as a percentage of the energy absorbed by the sun. Well, of all the sun's energy landing on the earth, 1 out of 4 parts is absorbed by living things, by green leaves and algae and so forth. So we have 100, 300 lost, 100 absorbed by the plants. Now, of that 100 absorbed by the plants, this is the efficiency. So this is the percentage of fixing as energy. In the laboratory, we can fix as much as 16% using sunlight. Sugarcane is one of the best and fixes 1.5%, which is not bad. As a matter of fact, that's average all round the year. Sugarcane, at its peak growing period, will fix as much as 4%. Now that's becoming a very high percentage, because after all, the sun is free. And the land average is much less, about 0.3%. And of that, we only use about 0.5% of that as food. So we don't use the sun very, very efficiently, do we? But let's have a look at something like sugarcane as a source of energy then. Here is a piece of sugarcane. It's a piece of grass. Sugarcane is a sort of grass. And that's one stalk of it. And it's very good stuff. Thank you very much. These are some sugar canes. And it really contains a lot of sugar. 1/4 of this is sugar. And I don't know how many of you have lived in countries. It's really jolly good. I don't know how many of you have lived in countries which grow sugar cane. For those of you who haven't, you might like to try some. Would you like to try some? Now, okay, yes. Now, we have lots of it, thanks to Reading University, who grew these for us. I think we have enough to give anybody who wants some a piece before you go home. But now, those of you who've got some now, the thing to do is to peel it like this and bite it. You see how much sugar there is in it. There is about, as I say, about 1/4 of that is sugar. And now, what is more, what what fuel? You remember we looked at the sugar molecules here. Do you remember how we grew how we can turn the sugar into power? Do you remember? Into other fuels? Well, what would you remember the champagne?
Fermenting.
Alcohol. You can make alcohol, and you can make half the sugar into alcohol. You can get half of your energy as alcohol. And alcohol will run a motor car with a little modification. In Brazil, where they grow sugar very efficiently, they are now trying to introduce 10%, even by law. You must have 10% of alcohol in all your petrol in your motor cars. So there's a great saving there. So this is one way, by fermentation of sugar and even of the bagasse, as it's called, or at least of the other carbohydrates here, one can get a lot of fuel. Now, there's another kind of fermentation. This makes alcohol, which is a good liquid fuel. There's another kind of fermentation which makes methane. I don't know whether have you ever stirred the bottom of a pond which has got stagnant and seen the gas come up? Well, that's methane, and that is made by little bugs. And this process is used on a large scale today, and has been, in fact, for some years, for the treatment of sewage. Sewage is unpleasant stuff. We want to get rid of it as quickly as possible, and if we can get rid of it quickly, all the better. And Mr. Needham here has this model was made by Mr. Warrington. Mr. Needham here has been looking after this for us. He brought it to the Royal Institution. It's been running for a month now here in the Royal Institution and making methane, and this is methane. The raw sludge is put in here, and this is the brew, so to speak. That's got the bacteria, a whole mixture of bacteria, anaerobic as they're called. They don't need air. They go on, in the absence of air, fermenting this sludge and making methane. And they've been doing so. Here's our gas bag. Here, I'm going to open. You see the methane running through here. And I hope this is methane and not a mixture of methane and air, because I'm going to light it. And there it is. And this has all been made from London sludge. There are one person, if you run it efficiently, one person produces a cubic foot a day, or the material for a cubic foot of methane a day, which is about as much as this, and the 8 million people in the London area need 100 million gallon capacity of these digesters. In fact, you see one perhaps here on your screens. That's the sort of size. There are 100 of those to treat all the sewage sludge in London. Well, that's the most beautiful sewage works you've ever seen, I'm sure. And it does produce useful fuel. It's enough fuel to supply the energy certainly for all the running of the works and so forth. Well, now that is taking those are examples of taking natural processes of fermentation which go on all the time. Now I want to see whether we can improve on nature in any way. Can we make the plants, after all, the plants were not designed for burning, were they? They weren't designed for us. Their interest really was in survival and propagation. A plant was designed to survive, stand up against the wind, and to reproduce and so forth. And it's far more complicated than we need, surely just to make hydrogen. We can do something simpler. Well, the next step is to break down the plant to some extent and then put it together again. Professor Hall here and Dr. Rao of King's College London are working on this, and they brought their apparatus to show us. Let me just first of all remind you of something we did before. You remember I said that in the photosynthesis process we have to transfer electrons or hydrogen atoms from water, here's water, from water to the carbon dioxide. Remember I said that? And that's going to make carbohydrate eventually. Now, I also said that I was only telling you, I was simplifying the story, and there are many, many intermediates, and there are. And one important intermediate is called ferredoxin. And in fact, the light transfers these electrons or hydrogen atoms onto the ferredoxin. And then the ferredoxin passes them on to the carbon dioxide. Now, Professor Hall is interfering with nature and short-circuiting this. He wants to make hydrogen. He wants to make the little plants make hydrogen. So he's short-circuiting them by using an enzyme called hydrogenase, which pulls off the hydrogens, the electrons, from the ferredoxin, takes them away, and releases them as hydrogen gas. Now, this would be the first time that plants have, in one step, you shine light on them, you get hydrogen. So what he does is to mix a hydrogenase, three things: hydrogenase, which he gets from bacteria in milk or red algae; ferredoxin, which he gets from that spinach. In fact, he gave me that spinach, which we were eating the other day. And as the plant, he extracts the heart of it, the chloroplast. Here's a picture of some chloroplasts, microscope picture. Remember, we saw a leaf, and we saw the chloroplasts inside the leaf. Well, he is able to extract those by churning up, cutting up the leaves, and then spin drying them, so to speak, centrifuging them, and get the chloroplasts out. So those are the three things, and they're in here, and I'll ask him to tell us, and actually, I hope, show us the hydrogen being produced. David.
Well, what we have here is the reaction mixture in this vial, which has the chloroplasts and the hydrogenase and the ferredoxin. And when we shine light on it, the chloroplasts split the water to produce hydrogen and oxygen. Now, what I'm going to show you is to take a sample from the gas phase above the liquid, and in this gas chromatograph, show you that it really is hydrogen and oxygen being produced. So I'm going to take a sample, 20 microliter sample from the gas phase, like so. And now this has been running for about an hour or two outside and has produced quite a lot of hydrogen and oxygen. I inject it into the gas chromatograph, like so, turn on this thing, and in about 12 seconds, you'll see one peak, which is hydrogen, and followed by that, the next peak will be oxygen. Now let's hope this works well. There's the hydrogen, and there's the oxygen, showing that water's been split in a light reaction from the chloroplasts activated by ferredoxin and hydrogenase.
Isn't that the quickest bit of chromatography you've ever seen? It was a chromatography as we saw before, but now it's done through a long column. Like this is a hollow column, and a long one, and the gas is passed through that and separated. How much gas do you get, Dr. Rao?
Produces a cc every hour in this vial.
About a cc an hour, which is not going to keep us going in gas at the moment, but this is a very small scale and can be scaled up. And it's a very hopeful process. It's the only process which actually produces hydrogen directly from plants. Thank you very much indeed, David. Now, the trouble is, as Professor Hall could explain to you if we had more time, the trouble is that those things are very delicate. They don't last very long. They're not breeding anymore. You've killed them from that point of view, so you have to keep replacing them. And it brings us back to the question, do we really have to use living things which are so delicate, which have to be fed on nitrogen and phosphorus and so forth? Although, of course, we can replenish this to some extent in that sewage sludge process that we saw. Of course, we can return, having taken out the methane, return the phosphorus and the nitrogen to the soil. But can't we make a leaf? Can't we make just the part of a leaf that we want? Never mind all the fancy stuff with the flowers and the branches and the tree and standing up against the wind. All we want is the essential part of a leaf which splits water and gives us hydrogen. Or better still, adds the hydrogen onto carbon dioxide and makes petrol and hydrocarbons and oil and all the goodies that we want. Can't we do just that? Well, if we're going to do that, we have to go back to the third lecture and think what a leaf looked like, what it was made of. What was the essential part, the essential structure of a leaf? Do you remember it was something like this? It was made up of membranes, themselves made up of these little fat molecules, lipid molecules with a watery head and an oily tail, proteins like this, lumps of protein stuck through them, and then two layers stuck together with the oily tails dissolving in the oily tails. Now that's a starting point, and I'm really talking about very primitive starting points at the moment. We're nowhere near making a leaf. In fact, maybe we never shall. It's said that only God can make a tree. We can try to make a leaf, but we're a long way from it. But let me just show you the sort of approaches we can have. So the first thing to do then would be to try to make a bilayer or monolayers or multilayers like this as the basis of it. And that can be done because Irving Langmuir, many years, half a century ago, showed how you can make one layer thick of molecules by putting oil on water. Not all oil on water, but if you put molecules like this on water, the oily tails don't like the water and they sit upwards, you see, so they sit upwards like that. Now, I can show you that first of all. Sheena Carlin here is doing research on making this type of layer, and so she's going to put the drop of oil on. Can you see? See, I put some powder on, lycopodium. Now she's going to put one drop in the center, just the right size, dissolve in a volatile solvent. You see that spread into a lovely circle. Now, that's on water, and I can do some experiments on it, but I do much better if I can transfer it onto a glass slide. And as I dip this in, nothing will happen. As I pull it out, I think you'll see it'll pick up part of the layer. Watch. Now watch. See it contract. And if you measure the area that has contracted, you'll find it's exactly the area of the two sides of the slide. It's picked that up. And you can go on doing this. You can make sandwiches. You can have another trough with chlorophyll or another lipid on it, another fat, and keep on doing this and build these up into these structures. But you can't really see that as a manufacturing process, can you? But what you can see as a manufacturing process is something even more complicated. And that's a vesicle. Isn't that a beautiful vesicle? Gareth Phillips, a new student here, made this for us. And it really is nice. And to make vesicles is terribly simple. I'll give you the recipe. You take some water, you add fat, and stir. That's it. Here we have a lump of fat. It's lecithin at the bottom of water. I'm going to shake, and you see it becomes milky. But if I now stir that vigorously with ultrasonic waves, I can break it up until it becomes quite clear. And here's one that has become clear, and this is something slightly different because I had chlorophyll in the fat. Now, chlorophyll is absolutely insoluble in water, and yet there you have a beautiful clear solution. It looks like a solution of chlorophyll in water. And the reason it's clear is that the chlorophyll is dissolved in the fat, which is in these vesicles in water. Now, these little things are only 250 angstroms in diameter. That's 1/20th of the wavelength of green light. Very, very tiny. You know how small that was. And that's what they're like inside. They have two layers of fat, and as before, as there, the oily tails are running one into the other. Now, you can treat these. You see that our problem is when we have irradiated something, split off electrons, they recombine. And the leaf gets over this by doing it across a layer of this kind. It pumps the electrons from one side to another. So if we make these with one solution inside and then wash them, we can put another solution outside. Here are the chlorophyll molecules, 1 and 10, 1 and 4 you can put in, shine light on and pump the electrons across. And this sort of reaction has been achieved, and there's a lot of research going on that at the moment. And you could make these on a chemical engineering scale in quite a big way. So I've talked to you about many ways in which sunbeams can be used to produce energy, and I now want to finish by asking, can we supply man's energy needs in this way? Well, first of all, we must ask what man's energy needs are. And I've got a ladder of energy here, which is in joules, and these are tens, so that is 10 times that, and that is 100 times that, and that's 1,000 times that, okay? Now, man at the moment uses just over 10 to the 20 joules per year. On the left, I've got the income and expenditure. This is expenditure, this is income of photosynthesis, that's future expenditure, that's income. And on this side, I've got capital of our fuels. Now, we've talked about gas and oil and coal, and you can see right away that we have less than 100 times what we use in 1976 of those. Let me just say, future up here is very hard to predict, and I'm no better crystal ball gazer than anybody else. But if we assume the population must go up to about 3 times what it is at present, 3 times 4 billion or so, you can't stop that, whatever. Maybe it'll level off at that, but it must continue for some time. Furthermore, the poor people in countries like India use only 1/30th on the average as much energy as we do, as the Western countries, and they're not going to like that. They want to have our standard of living. So the average consumption of energy per person has got to go up by a factor of 6 if everybody's going to have a reasonable standard of living. So that's 6 times 3, that's 18 times the future demand is a modest estimate, and that's not in the very distant future. So that's what I mean by this. You see, it's almost as much in, the demand is almost as much a year as the total oil and gas we have. Coal, a little bit longer, 150 years or so, as we said. Uranium, used for nuclear reactors, somewhat longer. Again, it's difficult to estimate how much uranium we have in the world. There's a terrific amount. There's a lot in the sea. But you get to the point, as you mine rarer and rarer deposits, get to the point where you're putting more energy in getting it out than you get out putting it in. See what I mean? So there is a limit. If that is an ordinary nuclear reactor, if we use a breeder reactor, which breeds its own fuel to some extent, then one can get 60 times more energy than this, and this would put us up here. But these, even then, are limited, you see. And there are problems about nuclear reactors. To do this, to satisfy our future needs in this way, would mean building 2 nuclear breeder reactors every day for the next 50 years. And they're very expensive, spread all over the world. We have, as you know, problems with the disposal of the wastes, and this would be a terrific amount of waste. And some people are not entirely happy that man has grown up enough, that he is sensible enough yet to be trusted with some 30,000 nuclear reactors, which after all contain the same materials, very similar materials to nuclear weapons. Well, these are problems that you have to listen to everybody, don't believe anybody, listen to everybody, and you have to make up your own mind. Everybody tends to be in favor of the sort of energy in which he is engaged or does research. So you have to listen to everybody's opinion. But suffice it to say that there are problems, and we would surely be unwise to rely on just that one source of energy. In case something goes wrong, and in any case it won't last forever. Well, what are the alternatives? The only alternative is nuclear fusion. This was nuclear fission. That is to say, the putting together of hydrogen atoms to make helium. There's so much hydrogen around, that is an almost unlimited source. And that would give us supplies way up here if we could do it with hydrogen rather than its isotopes. That's one. Now, there are two ways of doing this. One is to develop a nuclear fusion reactor on the Earth, and nobody has done that. People are working on it very hard, but nobody's got a single watt out of it. The other way is to use a fusion reactor which we all know very well and which works. What's that? The sun, a beautiful fusion reactor 93 million miles away, which works beautifully. And that is the possibility. Now let's see, let us assume that this is what we want to do and see what the possibilities are. Here we have the sun streaming in, and I want to show you a few figures. Here is the sun streaming in, and it gives us, this is the radius of the Earth. Across this, it gives us 1353 watts per meter squared. When it's gone through the atmosphere, that's 800 watts per meter squared, a little bit less. And what is that over the surface of the Earth? Well, the surface of the Earth is 4 times the circle, 4 pi r squared. So that's 200 watts per meter squared. Now, I'll show you how that's distributed in a moment. Now, we have to talk economics. We have to talk, I haven't talked about money much in this. This isn't the money program. I haven't talked about it much, but it is vitally important at this stage. A present power station costs us about £400 per kilowatt. Man is going to buy the cheapest power, in spite of all the dangers I've talked about. If two companies offer you electricity, one twice the other, which you're going to buy, the cheapest, you're not really going to ask where it comes from. So it has to be competitive on that basis. So if we're going to collect solar energy to do this, we have to be able to do it, spend on our apparatus £400 per kilowatt. Well, the solar power is 200 watts per meter squared. Let us suppose we can get 10% efficiency. We know we can get 13, 14, 15% from silicon cells. Suppose we can get that. Then it means that we can afford to spend only £8 per square meter. £8 per square meter. And that is what we have to do. To be able to do this economically, we've got to be able to build things at £8 per square meter. And it's a bit questionable whether we can do that. It's to be hoped that we can. It's a wonderful source. There is so much of it. The whole of our 1976 needs would be supplied by that amount of Earth's surface at 10% efficiency. And the future projected needs of that terrible world with all those people would need that much. Where are we going to put it? Well, these are contours. Obviously, the deserts have more than Britain does here. This is 300 watts, 350 watts per square meter, 300. Poor old Britain only gets 125. That's not bad. It's about a half of the deserts. But the desert areas of the world are 1/8 of the Earth's surface, and they're used for practically nothing else. These areas are not very different from the areas which are used to grow wheat, and energy is almost as important to us as food. But we have to get the cost down. We have to develop new methods. The best brains in science and in technology are needed, and they have to be devoted to these problems. And it's up to you, the next generation of scientists, to see that those problems are solved before the wells run dry.